Welcome back to This Explainer. Today, we are cracking open Chapter 3 of the legendary book, Designing Data-Intensive Applications, to unpack the fascinating evolution of data models and how we query them. You see, the way we structure our data dictates absolutely everything. It defines how we interact with it, how our applications perform under pressure, and ultimately how our businesses scale. This chapter breaks all of that down brilliantly, and I am absolutely thrilled to guide you through it. So let's dive into this fundamental question right out of the gate. As the source material makes super clear, there is an overwhelming variety of systems out there today. We're talking traditional relational databases, NoSQL data stores, massive data warehouses, highly specialized graph databases, the whole shebang. Navigating this maze isn't about finding the one magical, perfect database. It's actually all about mastering trade-offs. Every single model we're going to discuss today has very distinct strengths and weaknesses depending entirely on your specific use case. Here is our roadmap for today. 1. Relational versus document models. 2. Structuring data for analytics. 3. Navigating graph data models. 4. Event sourcing and CQRS. And 5. Data frames for machine learning. Section 1. Relational versus document models. We're starting our journey with the most ubiquitous system in the world, the relational model, driven heavily by SQL, and the major challenger that emerged over the last decade to address its rigid structure, the document model. Now, if you've ever written application code, you already know this pain intimately. The source borrows a term from electronics, impedance mismatch, to brilliantly describe why developers get so frustrated. It perfectly captures that awkward disconnect and the heavy translation layer required when you try to force beautiful object-oriented application code into flat, rigid relational database tables. We often use object relational mapping tools, or ORMs, to try and hide this mismatch, but they often do it imperfectly, leaving developers to mentally juggle both representations and sometimes, accidentally, write highly inefficient queries. Think about a standard LinkedIn-style resume. It actually perfectly illustrates the relational approach. To handle one-to-many and many-to-many relationships, like a single person holding multiple jobs at different organizations over the years, you're forced into using highly normalized, separate tables. You've got a main users table, a positions table, an organizations table, and they're all stitched together by foreign keys. Now, this design is incredible for preventing data redundancy and keeping things totally consistent. But it forces the database to perform joins to pull all that scattered data back together into one coherent user profile. Which brings us to the epic showdown regarding how these models handle their underlying structure. On one side, we have schema on write. This is the traditional relational approach. The schema is explicit, and it's strictly enforced the moment you write the data, kind of like static type checking in programming languages. On the flip side, we have schema on read, which is heavily utilized in JSON document models. Here, the structure is implicit. It's only interpreted by your application code when you actually go to read the data. This gives you incredible dynamic flexibility, which is an absolute game changer when your data structures are heterogeneous or constantly evolving over time. Section 2. Structuring data for analytics. As applications scale up and businesses start needing complex analytics across massive data sets, those operational transaction-focused models we just talked about, they hit a wall. And that leads us to specialized data warehouse structures optimized entirely for massive, fast read operations. To grasp analytics architecture, you really have to understand fact table. In a data warehouse, this is your beating heart. It contains massive, append-only logs of historical events. Think of an event like a customer buying a specific product at a specific time, or a user clicking a button on a web page. In a large enterprise, these fact tables aren't just big, they easily grow to petabytes of data holding trillions of individual historical records. Picture a star schema. You have that massive fact table sitting dead center, and it connects outward to dimension tables, literally creating a star-like shape. While the fact table holds the raw individual events, these surrounding dimension tables give you the context, the who, what, where, when, and how of the event. So a dimension table might hold the specific details of the physical store location, the descriptive details of the product, or the exact date and time of the sale, maybe even flagging if it was a public holiday. Now, what if you take those outer dimension rays of the star and splinter them even further? Say, normalizing a product dimension down into separate brand and category tables. Well, then you get what's known as a snowflake schema. This approach is great because it saves valuable storage space by reducing data redundancy, but honestly, it can be a bit of a headache for analysts to query because it requires executing significantly more joins. Section 3. Navigating graph data models. What happens when the relationships between your data points become vastly more complex than simple analytics? We need a completely different architectural approach. Whenever anything is potentially related to everything else, like social networks mapping out who is friends with whom, or a navigation system mapping routes between cities, relational databases just choke under the weight of endless joins. Enter property graphs. They allow us to store completely different types of vertices, like people and geographical locations, and edges, like lives in or born in, all within a single, highly traversable database. It's a remarkably powerful paradigm for mapping out highly interconnected, heterogeneous data. Closely related to property graphs are triple stores. Heavily influenced by the early semantic web movement, triple stores break data down into the absolute atomic structure of a simple three-part statement: subject, predicate, and object. It's literally as simple as Jim is the subject, likes is the predicate, and bananas is the object. It's an elegant, deeply flexible, and honestly pretty fun way to represent complex webs of facts without forcing them into strict tables or nested documents. Of course, navigating these complex webs requires highly specialized tools. You absolutely cannot just use standard SQL efficiently here without making your queries incredibly convoluted. We need declarative query languages, where you just specify the pattern of the data you want to find, rather than detailing the exact computational steps the database needs to take to fetch it. Understanding the nuances between tools like Cypher, Sparkle, Datalog, and GraphQL is absolutely crucial to leveraging graph databases effectively and traversing multiple hops through your data with ease. Section 4, Event Sourcing and CQRS. Now we pivot to a paradigm that treats data not as a static snapshot of the present moment, but as a continuous, immutable history of actions. Let's talk about event sourcing. Think about a shopping cart. Event sourcing conceptualizes data as an append-only log of immutable events occurring over time. Instead of just updating a database row to reflect the current state of a cart, you actually record every single user action. If an item is added, updated, and then finally removed, all three distinct actions are recorded sequentially. This means if a booking is made and later canceled, both actions exist forever in the log. It provides a flawless, undeniable historical audit trail of everything that ever happened in your system. But there is a very obvious catch here, right? Reading the current state from a massive append-only log every single time a user loads a page would be agonizingly slow. And that's exactly why we pair event sourcing with CQRS, or Command Query Responsibility Segregation. CQRS acts as the ultimate translator. It asynchronously takes those raw, write-optimized historical events and translates them into denormalized, read-friendly application states or materialized views. So you get the perfect write history on one side and the perfect read performance on the other. Section 5, Data Frames for Machine Learning. For our final paradigm, we really have to look at the heavy mathematical lifting required by artificial intelligence and scientific computing. As machine learning continues to take center stage in the modern AI boom, we rely heavily on data frames and column-oriented storage. Data frames essentially generalize relational data into massive matrices and multidimensional arrays. This provides a crucial, high-performance bridge between traditional database storage and the specialized, memory-intensive formats required by analytical AI tools. It proves, yet again, that the fundamental shape of your data must perfectly match the specific analytical work you intend to do with it. As this explainer wraps up, I want to leave you with this fantastic quote directly from the source material. Normalization and denormalization are not inherently good or bad. They simply represent trade-offs in terms of performance of reads and writes and implementation effort. I absolutely love this because it serves as a powerful reminder for all of us in software engineering. There is no perfect database. There is no magic bullet. There's only the correct architectural trade-off for your specific problem at your specific scale. Knowing the strengths and weaknesses of highly structured relational tables, dynamic and flexible document models, deeply interconnected graph databases, and immutable event logs, the choice is now entirely yours. How will you structure your information to build something incredible? Thank you so much for joining me on this deep dive into data models, and I'll leave you with that provocative thought to ponder for your next big project.